Yes.
Okay. Jawab menurut ghorban tadi. Pasti betul ghorban.
Hello and good afternoon, everyone. Today I'll be talking about my lovely project, which is fabricating the next generation scaffold for tissue regeneration. This topic is actually very similar to what Zakia was just presenting, but the whole concept is that I'm using a different technique with different materials of producing this. So currently, there have been a lot of materials being used, and there's immense research going on in tissue regeneration. So the reason why people are coming up with this idea is because for such a long time, people are using donor tissues to regenerate your, for example, liver, pancreas, intestine, and so many other tissues and organs. But the idea of this is so we can neglect the fact that we require donors to donate the tissues or organs. Now, the question here arises is, can tissue regeneration using material hybrids for scaffolds become reality? So many materials, currently so many polymers are being used, such as polyethylene glycol, polycaprolactane, and many others, collagen, gelatin, they've been using to fabricate these scaffolds. The idea, as Zakia explained, hers is to do with solvent leaching and solvent casting and particle leaching. But my project is carried out using 3D printing. So we're fabricating the scaffolds using a 3D printer. Now, as you can see, this is a powder, it's a ceramic scaffold fabricated for bone regeneration. My project really focuses on the bone regeneration part. Now, as you can see, this is just a general animation where, let's say you have a fractured bone, they take in that scaffold, they cultivate the cells in it, and they place it instead of that, where it regenerates the bone. Here are some samples I just showed you. You can press it on. These are the scaffolds. So basically, you take this piece and you implant it in between the bone, and it regenerates. The idea behind this is that these materials should have the appetite-forming ability, which is where the bone can form, because the bone has a lot of the composition of the bone is made from apatite, a chemical which is found in calcium carbonate and calcium phosphate. The idea behind the tissue regeneration is you have to have a very good understanding of the cells that you're using and the signals, because so even right now from donors, or you get from tissues from donors, once they're implanted, they can be rejected by the body. So there has to be a good signaling effect from the body towards the scaffolds. And the scaffold itself is very important in terms of its porosity to allow the exchange of metabolic and waste, and also the properties of the scaffold should be in a way where the cells could adhere and stick onto the scaffold, so it could allow for proliferation and differentiation of the cells. Now, this is basically what I was explaining about tissue engineering. The whole concept is to get rid of the lack of problems we have from tissue regeneration. And you have to have a very good understanding of the cell mechanism, how they react once they're implanted into the body. And you have to understand, what I mean by understanding the behavior of different polymer composites is basically, once these polymers are implanted, they all possess different properties. So you can't use the same material for bone regeneration as you would use for example, regeneration of the pancreas or other organs. So it's very important considering the materials you're using. This is basically it. You have your cell, you have the housing, which is the matrix. You cultivate it and you implant it into the body. Now, these are carried out in vitro and in vivo. In vitro is basically in a body simulated fluid, where the environmental area where it's set is very similar to the body fluid, and they want to see how the scaffold will react. Will it regenerate or not? And in vivo is in live animals. It's currently not been used in humans, but it has fortunately been used in animals such as pigs and rats, and it has shown the capability of bone regeneration. Now, the outline of my project. I'm going to be talking about my research objectives, literature review, experimental works, and finally my conclusion. Okay. Determining a method of mixing for the composite. As I'm going to be talking about later on about the 3D printer I'm using, the problem I'm having right now is I'm working with polylactic acid and calcium carbonate. The problem is once I melt the polymer and I want to add the calcium carbonate, you get agglomeration. So this material can't be injected easily because the nanoparticles of calcium carbonate are agglomerating at the nozzle, so it's blocking it. So it can't eject properly. This is the problem. I'm going to perform lab tests, as Zaki explained, the SEM, which is showing the porosity level and the mechanical properties, which I have not done yet because of some technical issue, but I need to carry out mechanical properties. And it's going to be carried out by a desktop robot-based rapid prototyping. This is a machine that's been made by Dr. Enamul and some colleagues, the 3D printing machine. The idea has been taken from the MIT, but it has been innovated into this 3D printing, which I'm going to show. Now, these scaffolds, they're very important to have high resorbability and osteoconductivity. Now, resorbability, there's a difference. The many polymers we have nowadays are biodegradable. That means in some environments they're broken down to their monomers and eventually disappear. Resorbability is the ability of these scaffolds to be broken down in the human body. So once this scaffold is implanted into the body, after some period of time, the body eats away these, for example, the polylactic acid is broken down to lactic acid and gone through the metabolic pathway from the human being. So as the bone is regenerating, the scaffold degrades, so there's no need for opening up the human body and removing the scaffold because it degrades automatically. And osteoconductivity, because I'm really focused on the bone regeneration aspect, so osteoconductivity is the ability of the scaffold to profilate and differentiate the osteoblasts. Osteoblasts are cells which are made specifically for bone regeneration. So if my scaffold is able to attract these cells and house them in order to allow for regeneration, this is the ideal scaffold for bone regeneration, osteoconductivity. Now, just a basic, because if I'm going to put all my literature review, it would be a few slides. Just a basic thing is, I'm working with polylactic acid and calcium carbonate. A very similar idea has been carried out with polylactic acid and calcium phosphate. But when I went through different journals, I noticed that the calcium carbonate has a better ability of forming the apatite. And apatite is, as I explained, the composition, that's the bone composition, the main composition of bone, which allows for regeneration. So since calcium carbonate has a better forming ability, it's believed that it would be a better scaffold. Now, addition of silver nanoparticles in my project is because right now silver ions are used immensely in different clinical applications because silver ions are believed to kill bacteria, the antibacterial. But nanoparticles, based on many research, shows that due to its size, it could actually penetrate easily into bacteria because of a smaller particle size. Therefore, it's been advised to use nanoparticles. And the other methods, there's Zakia explained about solvent casting. There's also electrospinning, which another group member is working on. These are all different ways of producing scaffold. My focus is going to be on 3D printing, like experimental work. Fiber-case scaffolds using polylactic acid, calcium carbonate composite. All right. Now the reason why I explained previously polylactic acid is because it's bioresorbable. I explained was bioresorbable and it's biodegradable. The problem is for bone regeneration, the polylactic acid unfortunately does not exhibit the mechanical properties of a bone. So when you reinforce it with calcium carbonate, you have the ability of strengthening that polymer. So you can use it for the bone because the bone has around 5 to 15 gigapascals of chemical strength. So calcium carbonate is the reason why we're adding it, and also because of its apatite formation. And silver nanoparticles, as I explained, is once this is implanted, we don't want the person to get any infection, so we use silver nanoparticles to get rid of that. Just now, as I explained, I had a problem with the premixing. So I carried, there are two methods going on, melting and solvent. So basically melting is just taking your polymers in a beaker, melting it to its melting temperature, adding the calcium carbonate nanoparticles and silver, and just stirring it, manually stirring it at around 220 degrees Celsius. This pre-mixing needs to be carried out because the 3D printer that's been fabricated does not have a stirrer inside the chamber. So that's why you get the agglomeration. If there was a stirrer in the chamber, it would just stir it, and there would be no agglomeration. But that's the reason why you need to have a pre-mixing technique. Solvent is basically just using a solvent. Every polymer has its own solvent. Dissolving it in a solvent, then adding the calcium carbonate and nanoparticles, mixing it, and then heating it up to the best solvent I've come up with is dichloromethane, which has a boiling point of around 40 degrees Celsius. So if you dissolve it in dichloromethane and add these particles, mix them, heat it up to 40 degrees, you will have that solid you want, which you can then insert into the chamber. I'll be showing you. Okay, this is once the silver nanoparticles, calcium carbonate, and PLA are mixed, you get this kind of grayish color. All right, this is the prototyping device Dr. Enamul has innovated. So basically, you have it's connected to a pressure. It's controlled. There's a computer. It's a CAD model. You design it on a CAD model, and it fabricates based on that. You have a heater, and this is the chamber. So basically, what happens is this can move in a 3 degree of freedom. It has 3 degrees of X, Y, and Z axis. This basically the polymers are inserted in here, controlled by pressure, the pressure vessel, and the heating. These polymers are ejected. The polymer just goes down, ejects the polyfilaments in the X, Y direction, and then gradually the Z direction is for the layers. So this is how you can fabricate these scaffolds. And the really advantageous thing of 3D prototyping is your interconnectivity is 100% in comparison to other. You have 100% interconnectivity. And studies have shown that the porosity level can reach up to 86%. But the issue over here is you have to have a well balance between porosity and your scaffold itself. Because if you increase the porosity, your scaffold in terms of the framework would be weaker. So that would affect the mechanical properties. So there should be a good control between porosity and the scaffold. This is the SEM images I've carried out. From close, this shows these are the porosity levels. In conclusion, I would like to say that polylactic hybrids are promising materials for bone regeneration, and 3D printed scaffolds of polylactic alga are showing good porosity rates. This sentence is very important because what I'm trying to emphasize is that tissue engineering may be practical currently because there's no theory on tissue engineering, as in there's no specific guideline showing as in the steps to get into like the implantation, but it's all practical based, and it's only been done, the maximum it has been reached to is the animal. It has not gone to human beings yet. So with this studies carrying out, this phenomenon will certainly become theoretical in the near future, where you'll actually have guidelines and books showing how this implantation can be carried out. Thank you.